Hello friends, today I will solve a LeetCode medium problem on arrays. So the problem is magnetic force between two poles. So it's given that in the universe Earth C137, Rick discovered a special form of magnetic force between two balls if they are put in his new invented basket. So Rick has n empty baskets and the ith basket is at the position I. Morty has m balls and needs to distribute the balls into the basket such that minimum magnetic force between any two balls is maximum. So Rick stated that magnetic force between two different balls at position x and y is absolute of x minus y. So given the integer array position and integer m, we need to return the required force. So we need to place balls in the basket such that the minimum magnetic force between any two balls is maximum. So let's consider the first example. We are given a position array, that is the position of baskets, and we are given m equal to 3, that is we need to place 3 balls. So this number line shows 5 baskets. So you can see the magnetic force between the balls at position 1 and 4 is 3. Similarly, the force between the balls at position 4 and 7 is 3. And the force between the balls at position 1 and 7 is 6. So the minimum magnetic force between any two balls is 3, which is the maximum. So if you try out any other combination, like you can see the minimum magnetic force will be less than 3. So let's discuss the idea about how to approach this problem. So we know that we have n balls, that is the length of position array, and we need to place m balls. So we have ncm combinations possible. So out of these many combinations, choose the combination such that minimum magnetic force between any two poles is maximum. So this will take n factorial upon m factorial into n minus m factorial time, and we can see it is not optimal. So let's discuss another idea. So let's discuss another approach that is based on binary search. So in this approach, first I need to sort the position array. So after sorting, all the positions will be in increasing order. Then we can say the position 0 and position n minus 1 can always contain a ball. So let's understand this statement. So for example, the first ball is at index I and the second ball is at index j, and we have index 0 and I is greater than 0. So if this combination is part of the result, that is first ball is at I and second ball is at index j. So in this case, distance will be position of j minus position of I. We can say this distance is less than position of j minus position of 0, because the array is sorted in increasing order. So from this we can claim that we can safely put the first ball is at index 0 and our result will remain same. Similarly, with this claim, we can say we can place the last ball, that is mth ball, at index n minus 1 safely and our result will not change. The minimum value of the result can be 1 when we place two balls adjacently, that is position of j minus position of I is 1. The second claim is the maximum result will be position of n minus 1 minus position of 0 upon m minus 1. So we know that after placing m balls, it creates m minus 1 partitions. As we need to maximize the distance between any two balls, so the maximum distance will be when all the balls are positioned equally between each other, that is any adjacent pair of balls are equidistant from each other. So the position of n minus 1 minus position of 0 gives the total range of positions upon m minus 1, that is the number of partitions. So this corresponds to the case when all the adjacent balls are equidistant from each other. So I will use binary search in the range minimum to maximum. So let's understand this with a given example. So after sorting, the position array will be here. The array is already sorted, but after sorting, the array will be 1, 2, 3, 4, 7. And I will do a binary search in the range. So the minimum result or the low is 1 and high will be position of n minus 1, that is 4, minus position of 0, that is the total range, total possible range, upon the number of partitions, that is m minus 1, that is 3 minus 1, which is 7 minus 1 upon 2 equal to 3. And initially I will set the result to 1, that is the minimum value. So now I will compute mid, or I will call it gap, that is equal to low plus high upon 2, that is 1 plus 3 upon 2 equal to 2. So now I will linearly check if using this gap, or if we place the balls using the gap value 2, can we accommodate 3 balls? So I'll linearly traverse the position array. In the previous slide I discussed we can safely keep the first ball at index 0. So here I'll run a for loop from index I equal to 1 till I equal to n, that is 4, because the first ball is placed at index 0, that is the position 1. Now for I equal to 1, the position is 2 and the distance between the first ball and the second ball is 2 minus 1, that is 1, which is less than 2. So I'll increment I. It means we cannot place the second ball here because we need the gap to be greater than or equal to 2. So now I'll go to next index, that is I equal to 2. Here the position is 3 and distance between current position and the previous ball's position is 3 minus 1, that is 2, which is less than equal to 2. So I can safely put the second ball here. So the second ball will be placed at position 3. Now I'll go to next index. Here the position is 4 and distance is 4 minus the index of the previous ball, that is 3, is equal to 1, which is less than 2. So I cannot place the third ball here. Now I will go to next index, that is I equal to 4. Here position is 7 and distance is 7 minus 3, that is 4, which is greater than or equal to 2. So I can safely place the third ball at this index. So the third ball will be placed at position 7. So with this gap, I can place all the 3 balls. So now I'll update the result to 2, and I know that 2 is feasible. So it means all the gaps less than 2 is also feasible. So now I'll increment the low to gap plus 1. So now the low becomes gap plus 1, that is 3, and high remains same, that is 3. So here I'll compute the mid or gap equal to low plus high upon 2, that is 3. So now I need to place the balls such that the minimum gap between any two adjacent balls should be greater than or equal to 3. So I'll place the first ball at position 1 or index 0. Now I'll linearly traverse from index I equal to 1 till I equal to 4. Here I'll compute the position is 2 and distance will be 2 minus the position of previous ball, that is 1, which is 1. It is less than 3. So I cannot place the second ball here because the gap is 1. But my gap requirement is it should be greater than or equal to 3. Now I will go to next index, that is I equal to 2. Here position is 3. So distance with the previous ball's position is 3 minus 1, that is 2, which is less than 3. So I cannot place the ball here. Now I'll go to next index, that is I equal to 3. Here position is 4. So distance with the previous ball is 4 minus 1 is 3, which is greater than or equal to 3. So I can safely place the second ball at this position. Now I'll go to next index, that is I equal to 4. Here position is 7 and distance is 7 minus the position of previous ball, that is 4, equal to 3, which is greater than or equal to 3. So it means I can place the third ball at this position. So now I'll update the result to 3. So next, I know that if 3 is feasible, then all the gaps less than 3 is also feasible. So now I'll increment the low to consider for bigger gaps. So now I'll increment the low to gap plus 1, that is 3 plus 1 equal to 4, which is greater than the high. So now I'll stop here. So the result will be 3. So now I will code the solution. First I will sort the position array. Then I'll declare two variables, low equal to 1 and high equal to position of n minus 1 minus position of 0 upon m minus 1, that is the number of partitions. Then I'll declare a result variable, that is initialized to 1, while low is less than equal to high. I'll compute the gap, which is same as the mid. So gap is low plus high minus low upon 2. So I am using this instead of low plus high upon 2 to avoid overflow. So now I'll check if gap is feasible to place all the balls. Then I'll update the result to the current gap. Then I know that all the gaps which are less than the current gap will be feasible. So now I'll consider for more gaps. So now I'll update the low to gap plus 1. Else, if the current gap is not feasible, that is we cannot place all the m balls, then I'll update the high to gap minus 1. At the end, I'll return the result. So let's write this is gap feasible method. So I have declared a private method with return type boolean. It's taking position array m and gap as the parameters. So now, so I have declared a variable called count balls that is initialized to 1. We know that we can place the first ball at index 0 or position of 0 safely. So I'll run a for loop. From index I equal to 1 till the length of the position array, and I'll declare another variable called previous ball index that is initialized to 0 because we know that the first ball will be at index 0. So if position of I minus position of previous ball index is greater than or equal to the gap, we know that I'll increment the balls count, that is I'll place the ball at index I, then I'll update previous ball index to I. So if the count balls becomes m, then I'll return true. If count balls cannot reach m, then I'll return false at the end. So let's run it for the sample test cases. Sample test cases are running fine. Now I'll submit it. So you can see it's working as expected. So let's discuss the time and space complexity. So this method is gap feasible. At the worst case, will take big O of n time because in this loop I am placing m minus 1 balls, and once I placed all the m balls I am returning. So at the worst case it will run n times, that is the mth ball will be placed at the last index. So this method takes big O of n time. Now here what we are doing, in this method within the while loop, every time we are discarding a half of the range, that is either low is increased to gap plus 1 or high is decreased to gap minus 1. So this loop will take big O of log of high minus low. So initially high is position of n minus 1 minus position of 0 upon number of partitions, that is m minus 1. So we can say this value at max will be, so here we are given position of I goes from 1 to 10 to the power 9. So this difference at max is order of 10 to the power 9 upon m. The minimum value of m is 2, that is m minus 1 will be 1. So we can say high will be big O of 10 to the power 9 or order of 10 to the power 9 in the worst case. So this while loop will take big O of log of high, that is log of 10 to the power 9. So it's close to 31. So we can say this while loop will run at most 31 times, and within the loop in each iteration we are calling this method is gap feasible, which takes big O of n time in the worst case. And initially we are sorting the array which is big O of n log n. So we can say the time complexity will be big O of n log n. So I have attached the GitHub link for this code in the description. Please do check it out. Thank you.